Hello everyone. We are from the Naxatra team. Please wait for some time. We will just start after a little bit.
Hello, can you hear me?
Yeah, ma'am.
Hello,
You are audible.
hello.
Yeah, ma'am, you
Yes,
are
yes,
audible.
yes,
Yes,
yes.
ma'am,
Okay.
you are audible.
Oh, sure. Okay, I shall share the screen. Um, One second. Um, is the screen visible?
Yes, ma'am. Thank you for
Okay.
joining us.
Yes.
I'll give a short intro. We'd like to warmly welcome our speaker, Dr. MC Ramadevi from Space Astronomy Group at the UR Rao Satellite Center, part of the Indian Space Research Organization. Dr. Ramadevi is a leading expert in X-ray astronomy with extensive experience in analyzing and interpreting data from space-based observations. She has a crucial role in developing and operating AstroSat, India's first dedicated multi-wavelength space observatory. Her work with AstroSat has significantly advanced our understanding of X-ray sources in the universe, including neutron stars, black holes, and active galactic nuclei. In this workshop, Dr. Ramadevi will be presenting on X-ray astronomy using AstroSat, providing us with valuable insights into the latest findings and advancements made possible by this remarkable mission. We are honored to have her deliver this session. Thank you. You may continue, ma'am.
Okay. Thanks. So, yeah. Hope the full screen is visible now. I'll just fit page. Fine. Okay. So, I will start with some intro basics so that the whole flow of my talk would be like starting off a bit of introduction of X-ray astronomy, how it started, and what kind of sources we have, and internationally what kind of missions do we have, and then how it started, and then AstroSat we have, and what are the instruments, basic info about AstroSat, and few of the select observations or results from AstroSat, but because AstroSat has done a huge contribution to X-ray astronomy, so a few results I will discuss, and then I will just give you a link wherein the data analysis help files are elaborately discussed. There was a workshop held um, to have a hands-on of workshop, hands-on of data analysis with AstroSat. So I shall leave you with that. So that is the flow of my talk. So to start with, mm, X-ray astronomy. When you say X-ray astronomy, basically it's study of X-ray celestial objects in the universe. And as everyone knows, we have to do X-ray astronomy in order to observe the class of sources. Cannot do it uh, with ground-based observations. Many of you would be familiar with the electromagnetic spectrum, wherein we have the visible, where and the observations of celestial sources with in the visible band happens with telescopes which are ground-based. So we also have space-based telescopes like the Hubble Space Telescope, which actually does optical observations in space, because there's a big difference in going to space to do astronomy, as the atmosphere becomes a large hindrance to do observations from ground. So why do we go to space for X-ray astronomy? Because X-rays are largely observed by Earth's atmosphere, and we need to go above the atmosphere and to carry your instruments way up to point towards these X-ray sources in the sky to observe. So this is a image showing a wavelength as a function of opaqueness, wherein you have to go above few 100 to 200 kilometers above atmosphere to into space, carry your instruments up there to do observations in X-rays. So initially, to in the domain of X-ray astronomy, there were proposals like there could be X-ray sources in the sky. Not only why should we limit our observations to optical, so we need to explore it, and so let us send instruments into space. So initial X-ray astronomy started with balloon borne experiments. When I say balloon borne, helium balloons which actually fly up, but there is a bit of attitude control options available. So when I say attitude control, basically pointing to a source or pointing in a particular direction, etc. There are means to handle it. And so instruments were carried to areas, open space, wherein they are tied to a balloon and flown into space. So, as I mentioned, it was a curiosity which drove to launch instruments into with balloons into space to take it above the atmosphere to observe the sky. So initially in 1960s, instruments were launched
Excuse me, ma'am.
in balloon.
Sorry
Later
to
on, it
interrupt,
was
ma'am.
taken. Yes,
Sorry to
yes,
interrupt, but there seems
it's
to be
okay. Tell
some
me.
disturbance coming from your mic, like some, like maybe it's too close.
Okay, okay, fine. Is that okay now?
Yes, ma'am. Yes. Thank you.
Okay. Thank you so much. Thank you for mentioning that it was really too close. Okay, so hope I'm clear now, correct?
Yes, ma'am. Yes.
Yeah, yeah, yeah. So, as I showed in the previous slide, we have to go to space. There were techniques to take the instrument above the atmosphere of Earth. Few were balloon experiments. Then there were also sounding rocket experiments. Like these balloon-borne and rocket experiments stay only for few. You can do experiments only for few hours. So the very reason of curiosity to find out if there is any X-ray source, X-rays coming from space, drove this idea of flying instruments into space. So in 1960s, a team led by Riccardo Giacconi sent a rocket to basically look for X-rays from the moon. So when they were actually trying to point to the moon, they got some enhanced X-ray counts observed in the detector, as shown in the picture here. So that was a sudden increase and a fall in X-ray counts. So as you see, the background is only 50 counts, and they found something like a factor of 7 to 8 increase in intensity in that particular direction. So later they realized that that is not the direction of the moon. The instrument was not looking at the moon, and it is something unique coming from some different direction in the sky. And this triggered X-ray astronomy. So they were curious to know what actually gave rise to this increased intensity, and not to the level of background. It is way too high and just increase and decrease within few minutes, during the flight of the instrument. And this basically increased the curiosity to find out what is actually driving this X-ray detection in space. So this fed a Nobel Prize for Giacconi for the first discovery of extrasolar X-ray detection. And so basically this observation uh, linked to already existing theories which said that there can be compact objects which can give rise to such high luminosities. So what is that? What basically drives this university? So according to the theoretical models, etc., which exist, there was a mention of compact objects which can actually accrete matter from a companion star or matter which is surrounding it, and this matter which falls onto the compact object can convert the kinetic energy, meaning the gravitational potential energy which actually the matter experiences, can be converted to very high temperatures, can be converted to kinetic energy and to high temperatures, giving rise to radiation in the domain of X-rays. So basically, this observation of SCO-X1, which was in the Scorpion constellation, the first X-ray source in the Scorpion constellation when it was localized, triggered the X-ray astronomy, which linked to initial origins of theoretical predictions of existence of black holes and neutron stars. So basically, it's gravity which gives rise to, which helps this emission of X-rays. So what does the X-ray system actually comprise of? So probably these are black holes and neutron systems. And how are these formed? These black holes and neutron systems. This is pictorial representation of a life cycle of a star. So what happens is the formation of this happens in a nebular region, wherein the matter coalesces, forms, comes to a stage wherein nuclear fusion gets triggered, and you get a normal star. And then over its lifetime, a star evolves. You would have heard of supernova explosions, wherein the star dies. It's an end stage of a star, which can give rise to compact objects, which means the core of the star can either can be left out in the form of neutron star or a black hole. So formation of compact objects, which are end stage of a star, have huge, very high intense gravity. These black holes and neutron stars are very compact, that the gravity of these stars are very high. And what happens is, uh, because of the high gravitational field, whatever matter surrounding this compact object gets accreted towards the compact object. And there are two mechanisms which have been predicted for mass transfer in these binary systems. When I say binary systems, you have two stars, wherein one star is a compact object and another is a companion, which could be a normal star which evolves over time. So what happens is, because the gravity of the compact object is very high, it starts to accrete or pull matter from the companion star. So there are two methods which are um, um, studied for the transfer of mass. One is this accretion through Roche-Lobe overflow, wherein the compact object accretes matter from the companion star, which actually fills its Roche-Lobe. Roche-Lobe is a gravitational potential, the region around the star till which its gravitational potential is felt. So any matter flowing beyond the surface of this Roche-Lobe will actually get pulled onto the gravitational potential region of this compact object, and the matter will flow in the form of circular region to form accretion disk, because these binary systems generally orbiting about a center of mass and will have an angular momentum associated with that. And so you will have matter getting pulled to the compact object and getting heated up to millions of degree Kelvin to get X-rays emitted from the region very close to the compact object. So another mechanism is that you don't have the companion star filling the Roche-Lobe, but you will have stellar wind coming out, throwing matter from the star, and thus this stellar wind gets accreted onto the compact object. So these are mechanisms by which X-rays are emitted. So the first discovery of X-ray in a extrasolar object, and the theories behind the emission of X-rays in different class of objects were linked together. And we had the first X-ray satellite, Uhuru, launched in 1970. So the first detection of SCO-X1 was in 1962, the first X-ray source which was detected. Following that, there were detections of few others, and then the X-ray community decided that we need to explore the X-ray universe, and let's have satellites which can stay in orbits to look at the X-ray sky to detect more number of sources. So the first satellite was launched in 1970s, and this discovered another X-ray source, which is Centaurus X3. Unlike the previous source, the SCO-X1, they just saw an enhanced in emission, and then meaning, when I say enhanced in emission, if you see, I will go back to the slide. If you see the light curve, you will see an increase in flux and then a decrease. So they found it, and it was back to the quiescent state. We call this quiescent state, but SCO-X1 is not a quiescent source at all. It is very variable. I will talk about different class of sources there. So most of the sources, X-ray sources, what we see is like they are not visible for most of the time, and suddenly they brighten up. So these are called X-ray transients. Okay, so this satellite, when it first pointed to the sky, it found a source which was found to have pulsations. When I say pulsations, I will link it to the lighthouse, which you people are very familiar. When the lighthouse beams towards you, you see an enhanced intensity, and then it goes off. So this kind of emission was seen in the source, wherein the increased emission, the light curve, when I say light curve, it's basically time versus intensity. So there were fluctuations in the form of pulsations. So when the period was analyzed, it was found to be about 4.84 seconds. And then for a source to produce this kind of pulsation, that should be rotating to that, meaning the spin period of the source should be as close to the values observed in the light curve. So this led to the discovery that only a neutron star can produce such kind of pulsations. Otherwise, if a normal star rotates to this level, it can rip apart. So X-rays were, and then there was another feature found in the light curve, and that the light curve showed pulsations, and for a while it was not seen, and then again it was observed. So this was linked to eclipsing binary. When I say eclipsing, the X-ray object, because there are two stars revolving about a center of mass point, when the one star goes behind when the compact object goes behind the companion, then you have a obscuration of X-rays, and you don't get X-rays. Then when it comes out, you get the X-rays again. So this period wherein you get a cutoff of X-rays and then back again actually helps in calculating the orbital period of the compact object in this eclipsing binary system. So this was found to be a binary system with the neutron star and a companion, which is a neutron star binary system. Then came various number of discoveries, one after the other. Like Uhuru satellite, there were many other satellites launched, and we have a different class of X-ray sources with studies carried out with data from different X-ray missions. So here I have put a few class of sources, like the pulsars, as I mentioned. So this plot here shows the actual observations of Centaurus X3. Centaurus X3, this is CEN, is basically the Centaurus constellation, and X3 is the third X-ray source. And this is a light curve observed by Uhuru satellite. And we have, if you see the plot, you will see enhanced X-rays gradually rising up and then falling down, and then it was not seen for a few days and then up again. So as you analyze the light curve from this X-ray source, you will be able to bring out various information about the X-ray system as such. And so we basically study these X-ray sources with different kinds of instruments and different techniques in X-ray astronomy to decipher information in these sources. So this is a light curve, which actually helps you find out that yes, this is a pulsar, which is pulsating with a pulse period of 4.8 seconds. And it is also an eclipsing binary because it goes off, and then the orbital period of the system is about 8 days. So this is another, the one on the right top, the neutron stars and white dwarfs. I've just put a few pictures of it to show that the compact object, when it is a neutron star system or a white dwarf, what you can have is the matter from the companion star can actually pile up onto the surface of the neutron star, wherein the matter, as it keeps piling, the density of the matter on the surface of the neutron star gradually increases, and finally it helps in X-ray outburst, trigger of an X-ray outburst due to hydrogen burning in the surface layer of the neutron star. So the matter being accreted from the companion star is largely considered to be helium, because on the surface of the star you have largely hydrogen, and then the matter accumulated onto the star piles up to a certain level, wherein a critical density is reached, where the plot here, wherein it is basically time versus intensity, which indicates this is an observation of a neutron star X-ray burster, H1735 444. These numbers for newbies, I would mention that these numbers, the way the X-ray sources are named, initially they were simply named as X-ray X1, X2, like SCO X1 is X-ray source number 1 in the constellation of Scorpius. Then X-ray 3, X3 is Centaurus constellation, and third source in that constellation. that constellation. But over time, they realized that there are umpteen number of sources which are discovered, many of them coming in queue. So they realized that numbering x1, 2, 3 may not be a good idea, and the sources were named with RA and declination. The RA, right ascension, and declination, which is basically location of these sources in the celestial sphere. Like how we have latitude, longitude, we have this location given in terms of right ascension and declination in the celestial sphere. And so these numbers, so I would be using this many quite often in the further slides, so I have to mention this, that the sources are named with right ascension, declination as. So 1735 is 17 hours 35 minutes, and minus 44.4 degree declination. So that is the way the sources. So X-ray pulsar, X-ray source, which basically shows, most of the time it is quiet, and suddenly you have an increase in flux, and then it goes off. This is a fast rise exponential decay as we define it, because the rise time is short and decay time is slow. So I'm giving this as an intro for such kind of signatures seen in X-ray sources in the light curve, wherein these have been identified to be X-ray bursts happening in these sources due to hydrogen burning happening on the surface of the neutron star. And these bursts exist only for few seconds. There are bursts which are seen from minutes and hours time scale, and that has been identified to be helium burning on the surface of the stars. So this kind of bursts are observed only in X-ray binary systems, wherein you have neutron star or white dwarf as compact objects. Largely, these are neutron star systems. So then we have this black hole X-ray binaries, which is shown in the left bottom corner. So black hole X-ray binaries. So X-ray binaries, as I say, they're all two body systems. One is a compact object, another is a uh, normal star, which is a companion star. So when the compact object is different, you have different kind of manifestations of the radiation coming from these sources. That is what I wanted to explain from the slide. So the first one, what we saw, pulsations. You need a very high magnetic field. I missed saying that. You need a very high magnetic field in order to get pulsations from a neutron star systems. When the magnetic field axis and the rotation axis are misaligned, only then you get these pulsations. So you can imagine, have a thought process later, that you spin the star along an axis, and you have a magnetic field which is inclined with a particular angle. The magnetic field axis is north-south axis. You will have the field lines running from north to south, and what causes these pulsations is that, I'm talking about this thing which I initially started with. I missed saying this, that's why I'm saying. So what causes these pulsations? You will have matter hitting the poles of the neutron star, and when the matter strikes onto the surface of the neutron star at the poles, it gets heated up to millions of degree Kelvin, wherein X-ray emissions are possible only at those high temperatures. So you get X-ray emissions from the poles of the star, very highly magnetized neutron star. At the poles, you get X-ray emissions, and if you have the spin axis or the rotation axis of the star and the field axis misaligned, then if you're observing star, you these kind of pulsing emission magnetic field axis get aligned to the line of sight. You will get the emission beamed, and when it goes off, when it is moving from these sources. So you need a very highly magnetized neutron star system to see these pulsations in these sources. And then these are less magnetized neutron stars, wherein you will have pole emission, but there is a possibility, there's a mechanism by which the matter gets piled onto the surface, because the ram pressure of the magnetic field region is not that high that it stops the matter from going to the surface. So as the magnetic field is low, the matter piles onto the surface, and you can have bursting signatures like this. So all what we have is the radiation from these systems, from which we do different analysis of the data to find out what is actually happening in these sources. So Now I have been talking about only light curves. So the pulsations are also defined from the light curve. The bursters is also the light curve, which is time versus intensity, which shows signatures. Then here I'm talking about the black hole X-ray binary, wherein signatures, evidence for black holes exists from the analysis whatever we have done, and it does not only limit to timing analysis, which is time versus intensity, the light curve. We go into more detail like spectral analysis, imaging analysis, as well as spectrometry, which I'll talk in the next slide. So there exists evidence for black holes from detailed study of the light curve and the energy spectra, and also go into Fourier domain of studying the frequencies coming from these systems. So we have these are strong X-ray sources, and they are very rapidly varying sources. And from the light, I'll show you some few light curves of these black hole binaries, how erratic they are. And when you do a Fourier transform of the light curve, you end up discovering quasi-periodic oscillations, which indicate mechanisms happening very close to the compact object, which is the black hole. Also, we find radio emitting jets from very close to the black hole. We have jet emissions coming from the center, and these are associated to black hole jets. Now, not only X-ray binaries, there are galaxies in the center of the galaxies. So the X-ray binaries, when I say, the mass of the black hole is like greater than 3 solar mass for it to be a black hole. This comes from the theoretical limit and studies which have been done from the degeneracy thing required for a compact object to be a black hole. And so for X-ray binaries, meaning stellar mass systems, you have mass of the black hole of the order of, we call them stellar mass because the mass of the black hole is of the order of solar mass. You explain it into few solar mass or few tens of solar mass. But when it comes to supermassive black hole, you can take the number, it's 10 to the power of 6 times the mass of the sun. So we call it solar mass is basically to define one unit, which is the mass of the sun. So we compare all the masses related to the mass of the sun. So the supermassive black hole has mass of the order of 10 to the power of 6 times that of the sun. So the black hole at the center, there is the discovery that there is a black hole at the center of the Milky Way galaxy, which is a supermassive black hole, which is 10 to the power 6. And there's a Nature paper which shows the discovery of this black hole at the center of our own galaxy. Then there are supermassive black holes wherein you have jets, and this is one image taken by Chandra, which is X-ray jets coming from a point wherein we have a supermassive black hole. It's a galaxy with a supermassive black hole in the center. So this, I've put a collage of different classes of X-ray sources, like how I discussed in the previous slides. We have this black hole binaries wherein the black hole is a compact object and it magnetized neutron star systems, wherein the magnetic field uh, um, matter flows along the magnetic field and you have emissions coming from the poles. You can also have magnetars wherein they are more pronounced in radio waveband. We also have X-rays coming from them. Then high mass X-ray binaries, these are basic. These can be largely neutron systems, but we do have black hole also as a compact object. So this, again, these are all come under binaries, the black hole binary, the high mass X-ray binaries. When high mass, low mass, the difference come from the mass of the companion star. So we do have neutron star systems as well as black hole systems, which comprise this high mass and low mass X-ray binaries. Then we have X-ray pulsars, wherein X-ray emissions, they are largely dominated by X-ray pulsations. The SEN-X-ray is one of them. And so you have a magnetic field and matter around it, and matter is channeled along the magnetic field, and you have a companion star with that. Then active galaxies, these are supermassive black holes at the center of a galaxy, which actually produce jets, and so they are called active. Then isolated pulsars, they are not an X-ray, they are not binaries, they are individual isolated neutron stars with very high magnetic field, which produce emission in the poles of the star. And we have supernova remnants, which are extended objects. Crab is a very standard source which is used for calibration of every X-ray instrument, because crab gives a more non-varying flux. It's always almost constant most of the time. And these are supernova remnants. These supernova remnants, extended objects, these are basically created when a supernova explosion happens and the matter is thrown out into the space, and you get such a picture. So these are different class of, and there are stellar X-ray flares which are seen, like sun, which gives solar flares. We have X-ray stars which produce stellar. What do we get to know from these kind of X-ray binaries? We get to know the high energy processes involved in these X-ray binary systems. So we get to know that black hole sources, galactic as well as X-ray galactic sources exist. Then we do measure the magnetic fields of neutron star systems, and we have a class of objects having different magnetic field intensities. Then the high energy process involved in the extragalactic systems, and then we discover new X-ray transients by observing the X-ray sky. And there is another aspect called an angular resolution, which again, with AstroSat we were having the UV as well as X-ray instruments in place, and UV was a state-of-art angular resolution, giving rise to deep field survey in UV. So my next slide would give you a feel of class of objects, neutron star systems, white dwarfs which are less than 1 solar mass, neutron stars are less than 3 solar mass, and black holes are greater than 3 solar mass. So what do we study in these sources? We have in the neutron star low mass X-ray binaries, we have the sources, bursters. I will explain each of these separately. So bursters, as I told in the few slides before, that matter gets accreted onto the surface, and you have bursts occurring from the surface of the neutron star, and you have certain oscillations coming from them. Then high mass X-ray binaries, wherein the magnetic field is very high, and you see them as X-ray pulsars. Then you have highly elliptic orbit B star orbiting a neutron star. We call it B X-ray binary neutron star systems. And then we have the black hole systems, wherein black hole is a compact object. And there is another class of X-ray binary system which is called the cataclysmic variable, wherein the compact object is a white dwarf, and you have accretion from a comet which orbits about the white dwarf. So these are the different class of X-ray sources study in each of these sources. What's the things which I discussed till now? And this is for you to have a understanding. As I told you, black hole binaries, if you see, unlike the neutron star systems, wherein neutron star do have such variabilities, but the X-ray bursts, what I showed in the previous slides, wherein these kind of X-ray bursts, which are fast exponential decay, which happen for few seconds to sometimes minutes and hours, do not happen in black hole binaries, because black holes do not have a surface. We have an event horizon as X-ray kept in orbits, and you do not have matter piling up on a. There is no surface, and there is no X-ray burst that can happen in black hole binaries. So light curve black hole binaries look. These are few class of few X-ray black hole X-ray binary light curves which I have put for you to get a feel that we do have different kind of variabilities seen in each of these sources. So the one on the right side is a typical X-ray type 2 burst which is seen in black hole binaries, wherein matter gets accreted via Roche-Lobe, and you have an accretion disk forming, and then the matter in the accretion disk can reach a critical density wherein it triggers an X-ray outburst, and you have the X-ray emission from this source, wherein the most of the time it is in quiescent state, and suddenly you have an increase and a decrease in intensity. Then there are other sources which have other features, like short recurrent bursts coming during the decay of an outburst. Then there are multiple peaks in the bursts, and then there are sources. Here you will, throughout the period of the source, you will find station in the light curve. This is another kind of profile of the curve wherein you have plateaued curve and a triangular outburst, etc. So now the question arises, like, what triggers this kind of different variabilities in these? And how do we understand these systems? So we are not limited to only timing analysis or only study of light curves. We need to take it a little forward to study the spectra of these black hole binaries. So when I say spectra, what does it mean? It is basically like how a light curve gives a variation of intensity over time. The spectra is the variability, the intensity as a function of energy. So what we do, we observe these sources, these class of sources in different energy wave bands. So X-rays, when I say, it's largely sub keV to few tens and hundreds of keV, kilo electron volt. So we do observe the sources, and then we model the energy spectra. The one shown here is basically study of the energy spectra with different components. So when I say model the energy spectra, we should have a priori idea like what is actually the emission which could be involved in that. So to tell you that the black hole binary emission largely happens from the accretion disk and matter surrounding the black hole, and we know that the accretion disks formed around the source can be considered as black body, multicolor black body, meaning multi black body emission. So the accretion disk shown here, you can have every layer acting, every layer here, every ring in this can have a particular temperature associated with it, and it can be a black body. So a combination of many of the black bodies together gives rise to a multicolor disk black body emission. So we model the spectra with that. And then we also have non-thermal emission, which could be inverse Compton scattering, which is coming from the plasma very close to the compact object. We call it a corona. So the X-ray emission expected in these by black hole X-ray binaries is largely thermal. This distribution largely broadly classified into thermal and non-thermal. So you have thermal emission coming from the accretion disk and non-thermal emission coming from the corona, which is matter very close to the compact object. So here there is a schematic which shows that you have a compact object at the center, and we have an accretion disk. And so the quiescent phase, which we observed, is largely we have very low counts, and as shown in this light curve, a typical light curve of fast exponential decay. So the system is mostly quiet, and then suddenly you have an increase in intensity. So how the system evolves over time is like it's mostly quiescent, and as matter from the component star keeps falling in, keeps coming in and accreting and forming the disk gradually grows closer to the black hole, and you have a very meaning fully grown disk which starts a hydrogen burning. It reaches a critical temperature. This is a disk instability model. There are many theories, many models to explain this emission coming from these X-ray sources. So one of that is disk instability model, wherein the disk grows closer to the object, and we have a critical density reached that triggers the burning of hydrogen burning throughout the disk and giving rise to and the temperature of the disk goes to millions of degree Kelvin and gives rise to X-rays. A sudden rise happens during the complete as the disk temperature grows much faster due to the burning of hydrogen or at a particular point in the disk, and then it grows and slowly decays. The decay phase is called the cooling phase of the disk. So this is one of the theories, but there are many other models which have come up. So we do the study of these X-ray sources happen in many domains. One is observation domain, wherein the data is analyzed with different models, and on the other hand, there is also theoretical models which are developed by theoreticians, and these go hand in hand to understand decades now by observing the different class of objects in different domains. It's timing as well as spectroscopy. So the one shown here is another method of seeing the evolution of the source. Basically, it shows like, there is a term called hardness ratio, which gives ratio of the flux in hard band to soft band. So we do study that also. So it's timing, energy spectra, the hardness ratio, and also observations of it in different domains, different wave bands to different wave bands to show a multi-wavelength study to see what is actually happening in these systems. So the pictures shown here are indicative of radio jets. These are, as evolves over time, we do have radio signatures in these sources. So when you observe the source in X-rays as well as in radio band, you will know that when the spectra evolves over time, you get radio emission only at some time, and then you don't have radio emission at the time. So this is basically to link to understanding what is the emission involved in these class of sources. So yeah, so black hole binaries we do study in timing and spectroscopy. And I will also introduce you to polarimetry, which is in one of the slides. So then X-ray pulsars and magnetars, these are neutron star systems wherein the magnetic field is very high. And we do, in the spectra, we do say, okay, I need to tell one more point here, that in the black hole binary, the spectra evolves with time. As I said, Bison phase, we have, I can link it to this plot here, wherein the spectra is largely hard. When we say hard, it is basically non-thermal emission coming in these sources. Non-thermal, largely inverse Compton scattering. Then, as the disk grows in and the disk contributes to most of the emission, then it is a thermal black multicolor disk black body emission, which in you can see in the spectral evolution here that the disk is the spectra is largely modeled with multicolor disk black body, which is a thermal component. That is how we know in these systems the system evolves over time. The spectral evolution happens as the X-ray flux increases and decreases in the light curve. So there is a tie of we do study in timing as well as spectral domain. Then when you this is another class of objects like X-ray pulsars and magnetars. Herein, if you see, say this is a neutron star, and if it is an isolated neutron star giving rise to X-ray emission, and it is called a magnetar, which because it's highly magnetized. And if you see the spectra, when you model it, it is very different from the black hole binaries. The black hole binaries largely it's the thermal component and the non-thermal, which is an inverse Compton scattering. But here, when you model them, it is like bremsstrahlung emission or synchrotron emission because the matter is actually gyrating the magnetic field lines, and you can also have cyclotron lines if you in X-ray pulsars wherein you have a companion star and a highly magnetic neutron star, you have signatures of cyclotron lines which can give rise to with which you can have an estimate of the magnetic field these stars. So this is again energy spectra for a X-ray pulsar, which is shown here. So now I have given you a gist of different class of X-ray sources and what kind of study we do in these X-ray sources. So this is one example of a Crab nebula, which I introduced you in few slides earlier. It is a supernova remnant, and it's an extended source. And this picture shows the Crab nebula in different wavelengths. So you see the optical, radio, far UV, X-ray. X-ray is taken by Chandra X-ray telescope. I will tell about the telescope in a few, not in detail, just introduce you to that telescope. It's a state-of-art telescope. Then the far UV and radio. So you can see that the image is so unique and different in different wave bands. All what you're seeing is the same source but in different wavebands. So this clearly shows that we need to, in order to understand these sources more in detail, what is actually happening in these sources and what are the geometry in these sources, we need to do observe these sources simultaneously in different wavelengths. And this is another picture which is basically observation of the Milky Way galaxy. Obviously, we are also in galaxy, but different. It's a mosaic of many images taken. And then, as you can see, different wave bands, radio, the 21 centimeter line, the radio continuum, the molecular hydrogen, infrared, mid-infrared, near-infrared, optical X-ray, gamma rays, it's all very unique. So this clearly shows that it is very important to have a multi-wavelength observation of any source to decipher the real mechanisms happening in those sources as well as the geometry of these sources. So, um, so to introduce you, there are many X-ray and gamma ray missions already in space, and these are a suite of instrument missions which I have just flashed here, like XMM Newton, which is a imaging instrument, which is highly there's a Chandra thing which has gone behind this. I'm sorry about that. So XMM Newton and Chandra basically do imaging of X-ray sources whichever it observes. Um, High resolution imaging, and Chandra can go up to sub-arc second resolution, which is state of art angular resolution obtained till date in X-ray waveband. Then the RXT, Rossi X-ray Timing Explorer. This is a X-ray spectroscopy and and timing. Then the integral in hard X-rays. So we have a suite of instruments which basically do study the X-ray universe in three primary domains, which is X-ray spectroscopy, X-ray timing, and X-ray imaging. So to add to this, what is India's role in the X-ray astronomy studies till date? So, X-ray astronomy in India started initially with sounding rockets from Tumba in 1960s. And later on, we also evolved to do this balloon flights, which happened from TFR's Hyderabad balloon facility, wherein instruments were carried in balloon. Then we had Indian satellites, the Aryabhatta and Bhaskara, carrying astronomy payloads. So these were piggyback instruments on various satellites. So this Ross series of satellites had, this is a picture of gamma ray burst instrument, this is scintillator detector. Okay, when I say about the detector for X-ray instruments, whatever we have today, there are a vast range of detectors, devices, which basically are used for X-ray detection. So we have gas-based detectors, we have scintillators, we have semiconductor detectors, which are largely silicon-based devices which detect X-rays. So this is one of the GRB experiment which was flown as a piggyback, and this is another. Yeah, it's a gas proportional counter which was flown on IRS-P3 mission, and this was also a piggyback instrument. Then we had solar X-ray experiment on GSAT, geostationary satellite 2, GSAT 2, which was a communication satellite, and we have few other instruments flown by foreign satellites. So this is how we started in India. We started X-ray astronomy by flying instruments in along with other primary instruments in various satellites with which we were doing limited X-ray astronomy science. Then we realized that it is very much required for India to progress to do multi-wavelength astronomy mission. So a dedicated astronomy satellite was planned, and that is AstroSat. So India's first dedicated astronomy satellite is AstroSat, and it has 5 payloads on board. I'll talk about the payload in the next slide. So it was launched in September 2015, and it's a low Earth orbit, altitude of 650 kilometers, and an inclination of 6 degrees. Usually, astronomy missions go for low inclination and low, as compared to polar orbits or any sun synchronous orbits. So we have 5 payloads on board the AstroSat, which are UVIT, LAX-PC, SXT, CSET, and SSM. I will talk about this in the next slide. And this mission is a collaboration of various centers, ISRO with IAA, TFR, IUCA, PRL, Indian Institute of Astrophysics in Bangalore, TFR in Mumbai, Tata Institute of Fundamental Research, Institute Center for Astronomy and Astrophysics in Pune, PRL in Ahmedabad, and CSA's Canadian Space Agency and University of Leicester were partners in developing 2 of the instruments here. So this is a picture of AstroSat, which is mounted in the ground immediately before launch. So to say here, the instruments, this one mounted here is the SSM. The one, this is SXT, which is a 3-meter telescope, soft X-ray telescope. Big 3 boxes are large area X-ray proportional counters, which are huge. Then we have the CCTI, which is sitting on the side. It's actually hidden. The radiator plate is behind that. So next is just to introduce you to all the payloads on board AstroSat. So we have 5 payloads. The ultraviolet imaging telescope, UVIT, it has 2 baffles, and it has 3 channels, 3 wavebands in which it does UV imaging, ultraviolet imaging. So the far UV in this range, 1 to 2 nanometers, 130 to 180 nanometers. And then we have the near UV channel, 200 to 300 nanometers. And we have the visible band, 320 to 520 nanometers. So this ultraviolet imaging telescope is an imager, which basically images the skies, images the objects which are pointed for observations. And tell you, it is the highest possible resolution achieved till date internationally, and we have the state of art UV imaging telescope as part of AstroSat, which has done wonders and brought out many science and added so much to the astronomy knowledge. So, but in the results here, I would only focus on X-ray observations, and further on the slides are pertaining only to X-ray sources. Then we have the large area X-ray proportional counter, which basically does X-ray spectroscopy and timing. So when I say X-ray spectroscopy is as I discussed in slides before, it's energy versus intensity, which is modeled with and studied. The spectra of the sources observed are studied in detail, and the timing is a light curve as well as the Fourier domain of looking for frequencies observed in these sources. And LAXPC operates in 3 to 8. Sorry, this is 80 kV. It should be 80 kV. I'm sorry about the typo. 3 to 80 kV, and we have this. Soft X-ray telescope, which does X-ray spectroscopy and imaging in the softer wave band as compared to the LAX-PC. LAX-PC is a broadband detector. Line spectroscopy is not possible with this, but however, soft X-ray has a better resolution as compared to LAX-PC. And soft SXT operates in the range 0.3 to 8 kV, which is softer as compared to the LAX-PC instrument. And then we have this cadmium zinc telluride imager, which has a larger field of view as compared to the other instruments. So to highlight, the UVAT, LAX-PC, and SXT have narrow field of view, like half degree or 1 degree, as compared to wide field images, which are CCTI and SSM. CCTI's field of view is 18 by 18 cross 18 square degrees, and it operates in hard X-rays, which is 20 to 100 keV. So as compared to SXT, you can compare the energy range. It is like few tens of keV, and SXT is in the soft X-rays and CCT is in the hard X-rays. LAX-PC does a overlap between the two, which is in soft to hard. Then comes the SSM, which is scanning sky monitor. Unlike the other four instruments are basically to do detailed study of each source it observes. They have a very narrow field and they look at one point, and they are all co-aligned. UVAT, LAX-PC, SXT, and CCT. The four instruments are co-aligned to look at one location in the sky. However, SSM is mounted on the yaw of the satellite. These are role pointing instruments. So SSM's field of view is completely different from all these point and mode instruments, and SSM is a very wide field instrument, which is shown here. So you have a large field of view, which is one axis it's 100 degrees, the other axis 20 degrees. Whereas in LAX-PC, as shown here, there are 3 units, and it has a collimator which collimates it to 1 square degree. And SXT here, it is half a degree with a very narrow field of view with a Volta 1 type mirror arrangement and a CCD at the bottom, which actually is at the detector plane. So and CCDI is a cadmium zinc telluride with a collimator, which collimates the field of view to 18 by 18 square degree. And UVIT has a detector with the filters arranged inside the baffle to cater to different wave bands here, and that also has a very narrow field. So I need to highlight one thing here. The suite of instruments here, every instrument is so unique, and every configuration of an instrument is very unique, as the science objectives defined for each are different. So LAX-PC is a gas proportional counter with xenon inert gas as the detection medium. SSM is also a gas proportional counter with argon xenon mixture. SXT is a semiconductor device as the detector, which is silicon based. UVAT also is that, and CSATI is cadmium zinc telluride as the detector. And UVAT has multi-channel plates also to detect the UV photon falling in, which is multiplied to produce electrons, and it is detected. Every photon is detected. That is how AstroSat does a multi-waveband imaging of the X-ray sky with covering the electromagnetic spectrum to UV to hard X-rays through soft X-rays. So coming to this table gives you a brief comparison of the instruments with energy range and possible time resolution and effective area. When I say effective area, this is how we compare the sensitivity or the detection possibility of an instrument with any internationally. So this is a picture showing the effective area of different instruments on board AstroSat, along with other missions which are launched till date. So now coming to like a summary slide, like different domains of astronomy. As I have told you, timing is one, spectroscopy, imaging, and polarimetry. AstroSat can do these three objectives: timing, spectroscopy, and imaging. However, polarimetry, although AstroSat was not meant for polarimetry, CCTA was able to do polarimetry of very bright sources, the GRBs, gamma ray bursts, and there are many publications which have come out of that. Also, we could do detection of from crab on board AstroSat. So yeah, so X-ray spectroscopy, timing and imaging, to tell you with delicate instruments. So this is one observation, first light curve from SSM, which is which it has observed a black hole X-ray binary, which is GRS 1915 plus 109, which is a very famous black hole. Showing beta class variability. If you go into the details of the source, you will understand that this is a very unique source which shows different kind of variability signatures in the light curve, and each and it has many different classes which are actually classified according to the profile of the light curve which is observed. And this is one observation showing that this profile uh, is the beta class of this black hole binary GRS 1915. And the one in the inset here is the RXT observation, which is done in 1990s by the NASA mission. And this image is a SXT plus lag species spectrum. As I told you, the energy range of SXT and lag species ranges from SXT 0.3 to 80 eV, and lag species has an overlap from 3 to 80 GeV. So this is a energy spectra of a black hole binary source which was newly discovered by MAXI during the time of AstroSat observations. MAXI J1535-571, and a combined spectra is analyzed here. And the same source timing analysis shows signatures of QPOs, quasi-periodic oscillations, which are thought to arise from the corona surrounding the black hole, a coronal region near to the black hole. And this is it's a first discovery of a QPO in the newly discovered source MAXI J1535. And this is a SXT image, soft X-ray imager on board AstroSat, and Cygnus X1 is another X-ray black hole binary, and SXT has observed, imaged the source. So these are the kind of science which we carry out with AstroSat. Now coming to, as I told you, three domains, which is spectroscopy, timing, and imaging, has been studied till date with all international missions which are launched till now. X-ray polarimetry is a new domain which we are venturing into, and first few measurements of Corab have been done in 1970s, and there was a big gap. And now Indian mission AstroSat has observed polarization Crab, and it has studied the faces of Crab Nebula, image of Crab Nebula, and IXP NASA has launched the polarimeter IXP in 2021, and that has brought many new discoveries of polarization in X-ray sources, different class of X-ray sources. And now at this point of time, we link polarimetry, spectroscopy, timing, and imaging, and we expect that we will bring a lot more new discoveries into the field of X-ray astronomy. To highlight, I would say Polix on ISRO's ExpoSat is a medium energy polarimeter which is launched in January this year, and it is second dedicated polarimeter mission internationally. So to say now, we come to the observations and results from AstroSat. AstroSat has done a lot of discoveries. It has contributed so much to X-ray astronomy with observations of different parts of X-ray sources, which I have been discussing till now. X-ray binaries, AGNs, galaxies, supernova remnants, stellar flares, etc., etc., etc. So this is neutron star bursters. As I already told you about the burst profile, we have fast rise, exponential decay. So how this happens, you have a hotspot on the surface of the neutron star, and that triggers a burning, hydrogen burning, and that spreads across the whole surface of the star. So this is a simulation shown here. Like you have a critical density obtained on the surface at one point, and then you have hydrogen burning happening
There seems to be a trouble with our speaker's network.
Hello, am I audible?
Yes, ma'am. Yes, you are audible.
Hello.
Yes, ma'am.
Am I on the same slide? Yeah, am I on the same slide where I left? Where I
Your
got
screen
disconnected?
is not shared, ma'am.
Oh, okay, wait. Yes, now? Am I on the same slide? Can you see the screen?
Yes, ma'am.
Hello?
Yeah. Yes, yes. We see neutron star busters. NS
Yeah, yeah.
busters. Yes.
Yeah. Did I get disconnected on the same slide?
Yes, yes. Now we are on the same slide.
Hello?
Yes.
Okay, fine, fine. So, yeah, so this is to say that we have, after AstroSat, we have the astronomy mission, which is ExpoSat, which has a polarimeter and a spectrometer in medium X-rays. And IXP of NASA does it in soft X-rays. So these are the dedicated polarimetry missions which have been flown till date. Then, so the results from AstroSat, I don't know whether I was audible when I said this. Results from AstroSat are huge. AstroSat has contributed a lot to astronomy. And with UV and X-ray payloads on board AstroSat, there are many things, many information, which and many publications which have come out for different class of X-ray sources as well as UV galaxies, etc. I would limit to only X-ray observations, and not all of them. Only few of the observations and publications which have happened in X-ray binary sources, because there are many of them which are listed in ISRO webpage as well as IUCA webpage, which any interested user can go in. So I'll briefly pick three class of sources and speak what AstroSat, few discoveries which have come out from AstroSat. So as I told you, the neutron star bursters, which are X-ray binaries again, the matter piles up on the surface of the neutron star, and you can have, when the matter gets heated up, there is a critical density attained at one point. You have hydrogen burning, which triggers the complete burning on the surface of the star. These are simulation pictures which are shown here. And so when the complete burning happens, you have an increased intensity, and this is observed as an X-ray burst from the neutron star systems. So unstable nuclear burning of the matter on the neutron star gives rise to thermo X-ray bursts. So during this X-ray burst, you can have X-ray oscillations. Oscillations, when I say, when you go to the frequency domain and you study the light curve in frequency domain, you will get certain frequencies which stand out, which are called burst oscillations. And this burst oscillations are seen to evolve over time. The frequency evolves over time. So next slide here shows a detection of millisecond oscillation, a high frequency QPO in these X-ray bursters. So this is a light curve, which is like, most of the time it is quiet and suddenly fast rise exponential decay, which is zoomed in to show here the fast rise exponential decay of the light curve. And when you study this light curve in frequency domain, you see this is a plot of time versus frequency, and you see the frequency evolving over time. And this frequency has been detected. The drifting frequency has been seen in frequencies from 315 hertz to 850 hertz evolution in the energy band 3 to 20 kV. And this is a detection in observed by LAX-PC. This data is from the frequency. We will be able to do this kind of timing analysis only with LAX-PC data. And the burst oscillation has been studied in this particular. Then we have this another, meaning this is one another X-ray burster for U 1636 minus talk. These numbers are coming from the array deck of the source. So there is a detection of rare triplet X-ray bursts. X-ray bursts usually have recurrence timescales. 1 minute, just give me a second. Just give me a second. Yeah, so these kind of triplet X-ray bursts are very rare, and we have very short recurrence time of 5.5 minutes between this. These are first detection of such kind of rare phenomena, and AstroSat has discovered that. And the same thing when you do the frequency domain study. So when we do such weak detection of 5 hertz with the signature, also with the signature of high frequency QPO. So this was observed to say that, and when the spectra was studied, it was observed that it is a hard state. So this kind of a recurrence time scale and 5 hertz QPO has been studied in hard state in these X-ray bursters. Then we have a class of systems, as I told you. We call these X-ray pulsars, where the magnetic field is very high and you don't have matter piling up on the surface, but it is channeled onto the poles of the star. So you have the magnetic axis and emission coming from north and south poles of the star, and the rotation axis of the star is inclined to the magnetic axis. Such X-ray sources, X-ray pulsars, we will be able to observe pulsations from these sources. So this is an illustration of a rotating neutron star pulsar with a high magnetic field. So LAX-PC has observed X-ray pulsars, and cyclotron scattering resonant features have been observed. What does that mean? So this is a X-ray pulsar source, and detection of cyclotron line is visible only if you do a energy spectra and model it with a Gaussian line. Then we see when the spectra was studied with light curve, there has been double peak instead of a single peak profile. So double peak pulse profile has been observed in this class of in this particular X-ray pulsar, and the evolution of pulse morphology is shown here. This is double, and after that it goes into single, and then it goes narrower. The pulse profile changes. So this plot along with the spectra, shows that the cyclotron resonance feature observed at 5 keV has a link to the double peak profile, pulse profile seen in the source. Also, from the cyclotron observed here, the magnetic field is computed to be 10 to the power of 11 Gauss in these sources. So, AstroSat has observed these kind of X-ray pulsars, many of them, and many discoveries have come up. This is another cyclotron line discovery in another X-ray pulsar, similar to what has been discussed in the black hole X-ray binaries. As I told you, here also we do a study of energy spectra and light curve and do the oscillation study in the timing domain. So there are many class of many list of black hole binaries observed, and this is a schematic which shows that what are all the components which we expect in such a black hole binary. You have the black holes, and then you have a corona surrounding it, and we have the accretion disk, the inner accretion disk. You have Keplerian disk at the center, and then you have a sub-Keplerian halo, wherein you have non-thermal emission. The Keplerian disk would be the contributor for the thermal multicolor disk black body in the sources. So as we observe many such black hole binaries, and here one of them is GRS 99105, exotic object, which has shown as compared to any other black hole binary, this has been very highly variable, and this is a plot, meaning it compares the GRS 915 to a few other black hole binaries, and the GRS 915, the Q evolution is shown here. It's basically timing, like converted to Fourier domain, we have the Q picture, and the high frequency being reported by with observations. So high frequency range from 67.2 to this exotic object. Newly discovered source Max discovered this source J1543 minus 5071. If you see the light curve, it's not visible, but this is very unique source which showed, we compare the flux generally with the standard X-ray source, which is Crab Nebula. Crab general intensity of the Crab nebula is considered as one Crab unit, and we compare the flux with all sources in that unit. The particular black hole source showed it was very bright, and it came to about 10 times the Crab, 10 or 8 times the Crab, and the energies and the timing analysis of this source, AstroSat discovered a QPO of the 3 to 20 keV range, and the spectral analysis of that is shown here. It shows a broadband spectrum thermal as well as non-thermal emission, and hello, am I audible?
Yes, ma'am. Yeah, you're audible, but the screen is not shared.
Okay.
There seems to be some internet issues.
Okay, probably at my end. I'm joining via mobile. I'm at office. I'm not able to. Yeah. Okay, so am I clear now?
Your voice is, but the screen
Hello?
is still not shared.
1 minute. Okay, now visible?
Yes, ma'am.
Hello?
Yes. Yes. The screen is visible.
Oh, okay. Sure. Okay. So, study of spectroscopy and timing together, we could pin down the origin of QPOs, which are arising from oscillating corona in these sources. So, this is another source, which is again a black hole binary, similar to the GRS 1915, which was discussed earlier. Here also, there are different class of variabilities observed, and we have found a double peak profile in the heartbeat class. So these terms you can just ignore, because for people who are not familiar with these class names, etc., it would be Greek and Latin. But if you, it is all to say that when you do a study of spectroscopy and timing together, you end up bringing up many new things and discoveries about the sources which we are studying. So although these class of these sources, whichever I'm listing, are studied so many number of times, especially the GRS 1915, which has been studied for many decades now, pin of the black hole, the variability profile, why such a variability is coming, and how it keeps changing, how are the different classes of variabilities. So that is how, in order to decipher things more about these class of objects and to understand the radiation mechanism, we have added one more domain of study, which is polarimetry, basically to understand the geometry of emission in these systems. So how exactly is accretion disk and the corona blend? Is that a simple multicolor disk, or is it like, as I told you in the previous slide, is it a Keplerian and sub-Keplerian disk together? So all these things are coming out of research which are done on the data observed from these sources. So this is another black hole binary. So if you see, the number of 4 different sources which I showed now, all what we do is study in 2 domains, which is spectroscopy and timing, and try to evolve out a scenario what is actually happening in the source. So this source observed by LACC, by doing the fitting of the spectra, we could find the spin of the black hole, and we have put an estimate that it is a maximally rotating black hole which has a spin of 0.92. So the black hole spectral modeling gives a constraint on the mass and spin, and we will be able to estimate mass and spin of the black hole by doing spectroscopy and timing. So by any new beginners in research, by seeing all these plots, need not be confused. It's all pertaining to spectroscopy and timing. So this is the spectra, this is a light, x-axis is light curve and y-axis sounds. And the last one here is hardness ratio. It's again a ratio of intensity in hard energy band, high energy band to a low energy band, to see how it evolves over time. This is basically as a function of time in 2 different energy bands. Then broadband modeling, the same energy spectra, which is modeled here, is like 2 different spectral states of the black hole, is modeled here to show that different components exist in different spectral state of the black hole. And this is a hardness ratio plot to show that how the system evolves in this domain. So all what we do is we accumulate or we observe the source, get the data, and do detailed analysis in different domains of X-ray astronomy, which is spectroscopy, timing, imaging, and polarimetry. So this is another black hole, which is black hole binaries. Few of them are shown, which are observed with AstroSat, and you can see the different types of variabilities in the light curve. Although these are all similar classes, similar. So the black hole binary, stellar mass black hole binary is a compact object, companion star with a companion star revolving around it. You have different types of profiles in the light curve, which shows that the mechanism, although it's accretion and gravity which is doing this job of X-ray emission coming in these sources, there are intricate details which differ from source to source. And this is one another source, which is a newly discovered transient black hole source. Discovery of QPO in hard X-rays has been done with AstroSat. So hard X-rays about 100 keV. This is the first discovery of a QPO in the hard band, such hard band. Now, I would last few slides. I would just speak about SSM on board AstroSat, because AstroSat, all the discoveries, whatever I mentioned till now, has been with pointed instruments on board, which is LAXPC, SX3, and CCT. SSM, as I told you, it's a unique instrument sitting on side of the deck of the light, looking at different part of the sky. It's just wide field, and primarily this is to do detect and locate X-ray transient sources in the very soft band 2.5 to 10 kV. So there are three modules which see different part of the sky, and this is primarily to detect and locate X-ray transients. So all these sources which I discussed till now, they are transient. When I say transient, I discussed the light curve also. Most of the time it's quiet and suddenly increases in intensity. SSM is basically to look at such sources and say, hey, something interesting is happening that source, and we give alert to the X-ray community to continue observations. So this is one of the observations of GRS 1915. This blue curve is the SSM observation showing the beta class variability in the sources, and this is a variation of the hardness ratio of the source which SSM could decipher. And this is another X-ray pulsar from which the pulse period, when you do the full frequency spectra of the light curve, you get the pulsations of this X-ray pulsar in just 3.6 seconds period. This is one another source which was observed in August 2021. This is maxi outburst, and follow-up observations were carried out with SM. And with this information given to LAXPC to continue a follow-up observation of the source. So it has observed many cloud objects, and these are the few astronomers' terrams observed. Only we few of them, because we limited with background, and only bright source observations were let out as astronomers. Pulsar, this is a black hole source. This is another black hole source in its faint state. And this is a neutron star binary, which was in an outburst, and astronomers' telegram was published. So these are a few pulsars observed with X1, crab, and 4U0115. Pulsations have been discovered in this, detected in these sources. So coming to the last slide, AstroSat. Am I audible?
Yes, ma'am. Yes.
The window is also seen?
Yeah, no, no, the screen is not shared.
Yeah, because I get this interruption saying the message from your server saying this is recorded and it disappears. Okay, so now?
Yes, ma'am. Yes, it's shared now.
Hello?
Yes, ma'am.
Yeah. Okay, fine. So, yes. So for all the students there, this huge amount of data exists with LAXPC, meaning with AstroSat. Many different class of objects have been observed, and if you were to download data or anything, you can go to
Excuse
this
me, ma'am.
website,
You were
which
not
is
audible.
basically 1 minute.
Yeah, can you repeat the?
Yes, 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 yes. So, am I audible now?
Yes, ma'am. Yes, now you're audible.
Okay, fine. So, the meaning if you have to download data from AstroSat archive, this is the web page which is shown here. Rather than noting down the web page, you can simply type in AstroSat space ISSDC in Google. You will get a few links wherein you can go on and check for AstroSat data. So one more thing, you will have to log in as you'll have to create a login account, and you will be able to log into the web page to see different class of meaning different data from different observations. Then for help file analysis, I was thinking of going through step by step, but that is not going to help a lot. So what I thought was this web page, which is basically a workshop which was held in 2021. It gives all the steps for all the payloads in AstroSat, how to do download the data, all the 4 instruments on board. SSM data is in a different web page because the objective of different continuous pointed observation. SSM data is not proposal driven. However, for AstroSat, if you want to observe a source, you need to write a proposal, and that is again hosted by ISSDC. If you type AstroSat ISSDC and go into that, you will have several pages for different objectives. Like if you want to submit a proposal, you need to go into AstroSat Proposal Processing System, APPS, AstroSat APPS. If you want to archive the data, this is the page. ISSDC has the archive, and these two are primary things which are required for AstroSat users. If you are an advanced researcher, you can always write a proposal to observer source and use the data from this archive to do further analysis. And for all beginners who are meaning you who want to venture into AstroSat analysis, help files are present in this web page, which is basically the tutors who have taught in the workshop have given an elaborate video as well as PDF file with steps involved in analysis of the data, which is very easy to follow. And so you can take this web page for all the data, meaning help files from this web page. If you need any further clarification, you can write to me. I can answer you. So you can take the email ID from the convener. So yeah, I end my talk with this. So overall, I've given you a gist of how X-ray astronomy began and what are the different class of sources in X-ray astronomy, which involves detailed study. What are the different domains in X-ray astronomy, like spectroscopy, timing, imaging, and polarimetry, and what details about AstroSat and what AstroSat has. Okay, one thing I must write here: I have not put all the results from AstroSat. It's very difficult to cover all of them, but the AstroSat support cell as well as ISRO page have details of discoveries from AstroSat. You can Google and get the information. If you say AstroSat support cell, Ayuka hosts it, and ISRO pages also have discoveries from AstroSat, which covers all of them, and the full list is given there. And yeah, finally, the AstroSat data help can be obtained from this web page. Thank you. Open for any questions if you want to.
Thank you, ma'am, for this wonderful talk. We express our gratitude for this amazing session. Now, I would request the participants to write any questions they have in the chat and ask us to unmute them if they want. Ma'am, we have our first question. Pranjal is asking, in burst stars, we are getting only a single peak generally. However, we are also talking about its frequency evolution. Could you please elaborate what is the frequency we are talking about here?
Okay. So I'll go to the slide to explain it better. So here, this is a bursting X-ray pulsar, and this is one X-ray outburst which is seen as a fast rise exponential decay. And when I say evolution of frequency, this is a time versus intensity. Okay, same thing. This plot here is also time versus the frequency. So if you see
Ma'am, the
every
slide is
segment,
not changed. The slide is still the same. The data analysis help you. It didn't change.
Oh, is it? Okay, okay. I will share it once again. Yeah. Is it visible?
Yes, Nish, it's visible now.
Yes. So you have this burst, which is time versus intensity, and the evolution of the burst in intensity, the intensity profile evolution is shown here. Now, when you go to the frequency domain, what you basically do is you segment small sections of this light curve, meaning you take data from different parts of this light curve and convert it into frequency domain, which is shown here. So one segment is studied in frequency, and you see the frequency profile. Meaning, then what you do is you study that different steps of the light curve. You do a frequency Fourier transform of this is the curve. And then you study the evolution, which is shown here. That is how you, so it's not a frequency in one outburst. You segment the outburst into many small sections, time bands, then separately study the frequency power density spectrum and fit the frequency profile of the PDS to find what is the frequency in that. That is how this is done. That is how the evolution is studied. Am I clear?
Yes, ma'am. He says that it's clear. We
Okay,
have
great.
another question from Abhishek. He's asking, does SAA apply only to low Earth orbit satellites?
No, SAA will be there for even high inclination orbits. See, it goes like you cut across SAA. Say in a, meaning I don't have an image to explain, but I just orally say, like SAA is like will have at a particular region on the sphere of Earth. So if you are in low Earth orbit, means you are almost like 6 degree is like almost equatorial orbit. You can consider like that. So you will only cross the SAA at certain time in the orbit. So when you are so in an orbit of say low inclination, low Earth orbit would be typical of the order of 90 minutes. So in the 90 minutes, you may have 10 minutes or 20 minutes SAA crossing, SAA passage, wherein the charge particle will be large and your data will be corrupted. So you will have to remove that data. However, if you go for polar orbit, meaning your inclination is going to be very high. So if you have 90-degree inclination, it's actually polar orbit. So if you go in polar orbit, you can have orbits wherein you don't cross SA at all, because you can be completely off the SA region. But when you are at certain orbits, you will have to cross through SA, and then you will have to remove your data. But one more thing to consider is, like in polar orbit, when you go to the north and south poles, you will have huge amount of charge particles, so in most of your orbits, most of the time of the orbit, you will have huge concentration of charge particle coming in the from the polar regions of Earth, which is not conducive for science missions. So you need higher duty cycle. When I say duty cycle, you need to have good data and long duration data. So best duty cycle possible is only done when you choose equatorial orbit, low inclination orbits in low Earth orbit. That is why we go for low Earth orbit. And yes, SA applies in low Earth orbit also, and some only at some part of the orbit will be affected. Yeah, email ID, conveners can share with the participants. And then,
Yes, ma'am.
okay,
Yeah, we
how
have
is the
shared the
spin
email.
calculated by analysis? Sure. And one question there is, like, how is the spin calculated by analysis of the X-ray profile? So I will go to one of the slides. I hope the slide is being shared. You can see the slide.
Ma'am, we can see the X-ray burst
Can you
hours
see the slide
slide.
changing?
Uh, yes, yes.
Same slide, huh? Okay, I'll share the slide again because I changed the slide. Can you see now?
Yes, ma'am. Yeah, it's visible.
Can you see now? Yeah, yeah. Okay. So this is one of the black hole binary where the spin estimates have been reported. So when you model the energy spectra with certain models which consider a certain parameter. So this was fit with the Kerr BB model, wherein the same time the blackbody temperature, emission, everything is taken care. So that from just fitting the spectral continuum of the X-rays, you will be able to estimate the spin of the black hole. This is one of the techniques. Is that clear? Okay, and then another question. Was that answered? Whoever asked. Anhad.
Yes, ma'am,
Yeah,
he
the
says.
next question is, okay, next question is a small doubt. Every time we said burning of hydrogen is accretion disk. Do we mean fusion of hydrogen to helium? Yes, yes, that is right. So it's basically fusion of hydrogen happens in the accretion disk due to achieving critical density. That comes from the disk instability model, which predicts emission of X-rays from the accretion disk. Then one another question, ma'am, how can we compensate the glitches and timing noise in timing analysis? When you do actual timing analysis, there are softwares available, and so there's no compensate glitches. Meaning, if there are glitches coming, the reference to consider that you have to. So, but there is the light curve, which can frequency in the timing domain, in the frequency domain. So, in order to handle that, the softwares, whatever we use in extreme timing analysis, takes care of that. We do consider that too with caution. Any other questions?
I think that is it for the questions. Once again, thank you, ma'am, for this session. I'm sure we all had a wonderful time learning new things.
Hello, am I audible?
Yes, ma'am. Yes, you're audible.
Hello. Yeah, okay. So I was not sure when I got disconnected. I answered the question. Hope that was audible.
Yes, ma'am. The answer was audible. And I think that was the
Okay.
last question.
Okay.
Yes. Thank you, ma'am,
Okay.
for
Yeah.
this session.
Yes. Yeah. Okay. Thank you. Okay. I can disconnect, right? Hello?
Yes, ma'am. Yes. Thank you.
Yeah. Okay. Okay then. Thank you. Bye-bye. Bye.
Thank you, everyone, for joining us for this session. We have another session by Dr. Shankar Subramaniam at 4 o'clock this afternoon, 4 p.m. to 5:30. So make sure to join for that. Thank you.